Hey guys, hope you're doing well. Coming back at you here with another video on number theory. In the previous video, we talked about how to solve a system of two linear congruences in two variables, very similar to solving a system of two linear equations in two variables. In this video, we're going to talk about how to solve a system of three linear congruences all in one variable. And just like the previous topic and the previous video, the topic we cover in this video, I don't have any handwritten notes for. There are other resources online, and you have your textbook. However, apart from those, this video is the other resource that you have. So consider this system of three linear congruences. X is congruent to A1 mod N1, X is congruent to A2 mod N2, and X is congruent to A3 mod N3. So basically, if you take the same number and take it mod these three different numbers, we want to come up with three different results. So how do we figure out what this X value is? Well, first of all, how do we know if we can solve it? All that is given and explained to us by the Chinese Remainder Theorem. The Chinese Remainder Theorem says that as long as the n values are relatively prime to each other, so n1 is relatively prime to n2, n2 is relatively prime to n3, and n1 is relatively prime to n3, then the above system has a unique solution modulo the product of these n's. It has a unique solution mod n1 times n2 times n3. Now, we could have a system of just two linear congruences in one variable. A system of two linear congruences in one variable, or we could have a system of four or more linear congruences in one variable. But for our purposes for this course, we're just going to stick to a system of three congruences in one variable x. The problem is a little bit lengthy and a little bit involved, but not too lengthy. But just so you know, the process that we're going to go through and see very shortly, it does scale up to a system of four or more linear congruences. As I said, the process for finding the x value that we're looking for is a bit lengthy, a little bit, and it is a little bit involved as well, but it's nothing too bad. So I'm going to try and break this down into a process with some nice steps here. First thing you're going to do is you're going to take the product of those n's. Take n1, n2, and n3, multiply those all together, and the number that you get then is what we'll just call little n. Once you find little n, we are going to calculate some other n values. These are capital N's, and they're capital N1, capital N2, and capital N3. Capital N1 is little n divided by little n1. Capital N2 is little n divided by little n2. And capital N3 is little n divided by little n3. So we find little n, and then we divide little n by one of the three little n values, and we get a corresponding capital N. We're going to take these capital N's and we're going to use them in our next step. Once you have the capital N's, you're going to set up and solve the following linear congruences on their own. This isn't a new system of linear congruences that we're solving. We just have three separate linear congruences that we need to solve on their own. And what these things look like, it's capital N1 x is congruent to 1 mod little n1. Capital N2 times x is congruent to 1 mod little n2, and capital N3 times x is congruent to 1 mod little n3. So these capital N's here become the coefficients in a new set of linear congruences. Again, not a system, just a new set or a new collection of linear congruences that we have to solve on their own. And these capital N's are typically fairly large values. And when you plug them in to its respective individual linear congruence, you may think, okay, I'm working with massively large numbers here. This is going to be a huge pain, but it's not usually bad because typically the capital N's are greater than its corresponding little n, and you can take these things mod its little n, and you can shrink those things down. When we go through some sample problems, we'll see how that works out. So, as we said, we want to solve each of these linear congruences on their own. The first, second, and third congruences will have solutions x1, x2, and x3 respectively. So x1 is the solution to the first one, x2 is the solution to the second one, x3 is the solution to the third one. What do we do with these x1, x2, and x3s? We're going to use those guys in the calculation to help us begin to find what our solution to the given problem was. So the solution to the system that we were given at the start is then given by x here, and this is the formula for x. X is equal to a1 times capital N1 times x1. Now keep in mind that a1 was just what x was congruent to in the first linear congruence there. Capital N1 we calculated, and then little x1 we just found. So it's a1 times capital N1 times x1 plus a2 times capital N2 times x2 plus a3 times capital N3 times x3. Each of these guys are whole numbers. You multiply them, you add them up, you're going to get some whole number. That whole number that you're going to get will be larger than your little n. You'll then take that x value, you'll take it mod little n, and what you're left over with, that is your final solution. And you could take that x value that you get and plug it into every one of your congruences in the given system, and you would find that if you've done your math right, then that would hold. That would make all three congruences true simultaneously. But this is very complicated and a bit confusing in just words. Let's go through some sample problems. Let's see how we actually use this process. So here's the first system that we're going to solve. X has to be congruent to 2 mod 3. It has to be congruent to 1 mod 5. And it has to be congruent to 11 mod 14. Note that these n values here, those are relatively prime to each other. 3 and 5 are relatively prime, 3 and 14 are, and 5 and 14 are as well. So we have a solution. Now let's go about finding that solution. First thing we're going to do is we're going to take the product of these n values here. 3 times 5 times 14 gets us 210. And then we're going to find each of our capital N's. Capital N1 is 210, our little n, divided by little n1, 3. And that gives us 70. Similarly, capital N2, little n divided by little n2, which gives me 42. And then capital N3, little n divided by little n3, and 210 divided by 14 gives me 15. So we're now going to set up three separate linear congruences that we need to solve on their own. It will be 70 times x is congruent to 1 mod 3. Again, we're still keeping the same n values. 42 is congruent to x, 42x is congruent to 1 mod 5. And then we're going to have 15x is congruent to 1 mod 14. Again, just sticking with those n values there. So we see we have 70, 42, 15. We have these larger numbers, but we can take these guys, mod its respective n value. And when you do that, things really simplify out, and things turn out to be a lot nicer than they may seem. Take 70 mod 3, you get 1. Take 42 mod 5, you get 2. And take 15 mod 14, you come up with 1. So these three individual congruences reduced come out to these guys here. And the first and third ones are the nicest possible case that we can have, because a simple reduction tells us what the solutions to the first and third congruences are. This is the best case we can possibly see. We only have to do a little bit of work on that second one, and it takes very little time to figure out what the solution to that second congruence is. So, as we said, the solutions to the first and third congruences are given to us right away. It's not too hard to see that the solution to the second congruence is x2 is congruent to 3. So we have our three solutions. x1 is congruent to 1, x2 is congruent to 3, and x3 is going to be congruent to 1. We're going to use these x values, as well as the capital N values, as well as the a values that we were given at the beginning of this question to figure out our x value. A1 was 2, capital N1, 70, x1 from above is 1. A2, 1, capital N2, 42, and x2 was 3. A3, 11, capital N3, 15, and x3 was 1. When you take those products and when you add those things up, you come up with 431. But we need to take that 431 modulo the 210, the product of our small n values, or we're taking it mod just our small n. And 431 mod 210 gives us 11. And you could verify this if you plug this back into your given system. 11 mod 3 is 2. 11 mod 1, or sorry, 11 mod 5 is indeed 1. And 11 mod 14 is just itself. So in this case, we came up with a relatively low value for x. Solutions are not always going to be that nice. The next problem we'll see, we're going to come up with a bit of a larger value. But still, it is a valid answer. Yes, we did do seemingly a lot of work to come down to a nice low value. Maybe this one, if you did a little bit of trial and error on your own, you could have found it. But not all such problems will be that nice. So here's another sample here. This one has a little bit more work involved. You're going to see that we'll be working with some significantly larger numbers here. So I have x congruent to 5 mod 8, x congruent to 3 mod 9, and x congruent to 18 mod 25. Again, just checking here, 8 and 9 are relatively prime, so are 9 and 25, and so are 8 and 25. So we're all good there. We do indeed have a solution. Taking the product of these n's here to give us our little n of 1800, and then we're finding our capital N's. Capital N1 is 225, capital N2 is 200, and capital N3 is 72. We're going to use these guys, and they are going to become the coefficients of x in each of our 3 resulting linear congruences. So 225 is, 225x is congruent to 1 mod 8, 200x is congruent to 1 mod 9, and 72x is congruent to 1 mod 25. Again, we are working with larger numbers here, but we can reduce these things. We can simplify these things by taking them modulo their respective n value. The first one becomes really nice. 225 mod 8 is just 1. 200 mod 9 is 2. And 72 mod 25 is 22. So we come down to these 3 equations right here. The first one, it gives us our answer. X is 1. That's perfect. The second one, 2x is congruent to 1 mod 9. Not too complicated to figure out what the solution to the second congruence is going to be there. The third one is a little bit nastier. It's a little bit meaner. But if you do a little bit of work with that third one, it may take you a little bit of time, but it doesn't take you too long to find out that the solutions to each of our 3 linear congruences there are 1, which we saw right away for the first one. Solution to the second one is 5, and the solution to the third one is 8. And you could say equals 1, or you could say is congruent to 1. Really, for the purposes that we're using these numbers for in this problem, saying equals versus congruent to is a really insignificant fact here. We have these solutions to each of our 3 individual congruences. So we do some calculations. A1 was 5, capital N1 was 225, X1 was 1. And then repeating A2, capital N2, X2, A3, capital N3, and X3. Take the product and add those up. You come up with 14,493. But we need to take this guy modulo 1800, because those were the products, or because that was the product of each of our smaller n values, 8 times 9 times 25. And when you take that number, 14,493, take that mod 1800, you wind up with 93. And again, you could check if you want. 93 mod 8 does indeed give you 5. 93 mod 9 does indeed give you 3. And 93 mod 25 does indeed give you 18. So that is our solution to this system of linear congruences. So this is how we use the Chinese remainder theorem and the process associated with it to solve a system of specifically 3 linear congruences in 1 variable. So this actually wraps up chapter 4. In the next video, we are going to talk about a couple fairly important results in theory of numbers Fermat's theorem and Wilson's theorem, and we're going to see how they relate to congruences of numbers. If you have questions or comments, be sure to drop them in the comments section below. Otherwise, until the next video, take it easy, guys.